logarithms are the family of functions that act as the anti-functions to the family of exponential functions. So the same way that a square, x squared, can be undone by square root, and sine can be undone by arc sine, etc., we need a set of functions to be able to undo this type of equation. Because up until this point, we've had to guess and check. You try 2 to the 1. Well, that's 2. That's not enough. 2 squared is 4. 2 cubed is 8. Ah, this must be 3. But I would rather have a function that could evaluate this so that I don't have to do all this guessing and checking. And so that's what these logarithms are for. The way you would write this is log, and then you need some sort of base here. And the base is going to tell you which type of exponent it undoes. So if I put in a log 5 here, that tells you that it undoes 5 to the x. If I put a 6 here, it undoes 6 to the x. If I put a 2 here, it undoes 2 to the x. So looking at this particular equation, if I need to undo 2 to the exponent x, I'm going to require log base 2. Those two functions undo each other. But as with all things in algebra, if I apply it to one side, I have to apply it to the other. Now looking at this side, because log base 2 and exponent base 2 are anti-function pairs, they end up undoing each other. And all that's left on the left-hand side of that equation is x log 2 of 8. Now, depending on which cell phone you have, some of the built-in scientific calculators on some of the cell phones have a log base 2 button, and you can just type that in. So if you were to do that, log base 2 of 8 ends up giving you 3. So that's how we're going to use it. I need to go over a little bit more of the details about what a logarithm looks like, how you construct them, but this is the goal, is using them, this new function, logarithm, in order to undo exponential equations. So antifunctions are reflections of their function partner. So I'm going to draw 2 to the exponent x for you, and then we're going to use that sketch in order to generate the graph of log base 2x. So the basic pattern for an exponential, you start at 1, this 2 to the exponent 0 is 1, 2 to the exponent 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the power 4 is 16, 9, 10, 11, 12, 13, 14, 15. And I have run out of space on my graph. Now over on this side, 2 to the negative 1 is a half, 2 to the negative 2 is a quarter, etc. So we have this asymptote over on that side. And if I connect all my dots, I get a function that looks like that. So what I'm going to try to do in order to draw for you the function log base 2 of x is I'm going to find the line y equals x here. I'm going to dot it in for you. And I'm going to take my 2 to the exponent x function and I'm going to reflect it across the axis. So this point right here, this was 0 on the x and 1 on the y. In order to reflect it, across the line y equals x, all I have to do is reverse the coordinates. So instead of 0, 1, I'm going to do a dot at 1, 0. So 1 on the x, 0 on the y would be here. See how this dot, this one there, is now here. This blue dot here was at 1 on the x, 2 on the y. So my new my reflected dot will be at 2, 1, 2 on the x, 1 on the y. This dot was at 2, 4. So my new dot will be at 4, 2. 1, 2, 3, 4, 2. And then I will have 8 and 3. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And 16 and 4. 9, 10, 11, 12, 13, 14, 15, 16, and 4. Now this dot here, this first one in the negatives on the x, that was at -1 on x, 1/2 on the y. So if I flip those around, I end up with 1/2, -1. So that would be here. And then the next one would be at 1/4 and -2. And then 1/8 and -3, etc. So I end up with an asymptote here, but it's not horizontal, it's vertical. I end up with a function that looks like that. That is log base 2 of x. So we're going to do a whole bunch of things to this function throughout the course. We're going to translate it, moving it up and down. We're going to stretch it this way. We're going to stretch and compress it that way. We're going to use it to solve equations. But for now, we should spot some features on it. You'll notice that this particular function has an x-intercept right there. So log base 2 has the following features. An x-intercept at x equals 1. Do you notice that it does not cross the y-axis? So there's no y-intercept. And it doesn't have a y-intercept because it goes vertical along the y-axis. And there's a word for that. That's an asymptote. But instead of being horizontal, it is a vertical asymptote. So these three features are the key things that you need to keep an eye on when you're trying to sketch a logarithm. So based on that, if I were to try and write the domain and range of this new function of log base 2, the domain then, domain is the set of all the x's such that, well, you notice looking along this axis, the function starts at 0 and goes this way, and there's nothing over in the negatives. So these x's all have to be greater than 0. Now there's a question about whether it's greater than or equal to that. In order to be equal to it, it would actually have to cross the y-axis, and we just said that it doesn't have a y-intercept. So I'm going to leave it at this. The x's must be greater than 0, and they should all be real numbers. As far as range is concerned, this tail goes all the way to -infinity, and this end, while it doesn't seem to be getting there very quickly, is in fact rising all the way. So it will eventually go all the way up. So there are no restrictions on y for the range of this function. Now, if you were to think about the exponential, which is what we based this on, the domain of an exponential is unrestricted. The range of an exponential is anything greater than 0, not equal to, greater than. Do you notice that that's the same as this, but reversed? So that's true about any function, anti-function pair. The domain of one is the range of the other, and the range of the first is the domain of the second. So you can keep that in mind. So to try and connect the logarithms and the exponentials numerically, to try and give you an idea of what this function means, I'm just going to start with a list of powers of 2. So 2 to the exponent 0 is 1. Anything to the exponent 0 is 1. 2 to the power 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4 is 16, etc. If I go the other way, 2 to the negative 1, now this is something you should have covered in grade 11, is 1 over 2, which is a half. 2 to the negative 2 would be 1 over 2 squared, which is 1/4. 2 to the negative 3 would then be 1 over 8. 2 to the negative 4 would be 1 over 16. Right? So these same numbers are just in the denominator of a fraction. So I have these powers of 2 over here. So I'm going to write the similar statements in logarithms. So if I were to ask you what the log base 2 of 1/4 was, it's asking what exponent would I have to put on a 2 to get negative 4. So see how these base 2 and 1/4, this is the number that's missing. So log base 2 of 1/4 should be negative 2. If I were to ask you what log base 2 of 4 is, because 2 squared is 4, log base 2 of 4 must be 2. 2 squared is 4. For this one, log base 2 of 8, because 2 cubed is 8, then log base 2 of 8 should be 3. Log 2 of 16, because 2 to the power 4 is 16, log base 2 of 16 should be 4. You see how I'm just returning the exponents on my powers of 2. So flipping to the base 3 exponentials, if I'm asked to evaluate this, log base 3 of 9, then I'm going to have to look at my base 3 exponentials. I'm going to have to find 9 in it. So because 3 squared is 9, my log base 3 of 9 should be this exponent, should be 2. Log base 3 of 1/9. Well, I find 1/9 in my powers of 3, and I find a negative 2 as the exponent there. So log base 3 of 1/9 should be negative 2. One more on here, log base 3 of 81. Now 81's not on my chart, but I'm asking myself what the exponent would be. So down here, if I continued it, 3 to the power 4, so that means take this number and triple it. Triple 20 would be 60, triple 7 would be 21, so 16, 21 is 81. Ah, there it is. So because 3 to the power 4 is 81, then 3 to the power 4 is 81. Do you notice that this logarithm was able to spit out positive numbers? It was able to spit out negative numbers? But I haven't tried putting a negative number in. So I'm going to try that one. ask myself what the log base 3 of -1/3 would be. So I'm going to go look at my list, and I'm looking up 1/3, and I found 1/3, but I did not find -1/3. And it's a weird trick about exponentials that when you take something and you raise it to a negative exponent, you do not get a negative number as your answer. So if I go hunting for negative numbers in these lists in order to convert to the appropriate exponent, there are no negative numbers in these lists. So this function here, trying to apply a logarithm to a negative, is undefined. It'll pop up on your calculator as error 1 or error 2. We call that a domain error, which we'll get to later. Because you've tried to shove a number in there that the function just can't work on. And if you were to rewind the video a little bit and see the sketch of a logarithm function, it looks something like this. Had a vertical asymptote here, and then it took off like that. Do you notice that -1/3 on the x is over here, where that function doesn't exist? So you can't put a negative number in here for a number of reasons. Two ways to think about it is that these exponents don't generate negative numbers, so you can't look this up in the list. Or this function doesn't exist over in the negatives, so you're not going to be able to pop one into there. So when you are presented with a logarithm acting on a number, it's sort of important to figure out exactly what this is asking you. So because the logarithm undoes exponentials, what this is asking you is, what exponent would you have to put on a 2 in order to get 16? So where am I getting these numbers from? This thing is log base 2, right there. So it's what exponent would you have to put on a 2 in order to get 16? So you go through the list of powers of 2 to see if you could find one. So 2 to the exponent 0 is 1. 2 to the exponent 1 is 2. 2 to the exponent 2 is 4. 2 to the exponent 3 is 8. 2 to the exponent 4 is 16. There it is. You would have to raise a 2 to the power 4 in order to get 16. So the value of log base 2 of 16 is 4. This number to that exponent equals this. Which leads to an interesting feature of logs and exponentials, is that you can flip back and forth between the two forms in order to see if you can solve them more easily. So this one, if I were to reinterpret it in exponential form, so in exponential form, maybe make the arrow a little longer there, says 2 to this exponent equals that number. 2 to this exponent equals that number. Lovely. So to interpret this particular logarithm, I've changed the base to a 3, and I've changed the number we're acting on to 27. The phrasing then in English would be, what exponent would you have to put on a 3 in order to get 27? So that's what that sentence is saying in math. If I were to try and flip it to exponential form, this would look like this number to that exponent equals 27. So 3 to the exponent x equals 27. So if this is the question it's asking you, what exponent would you have to put on a 3 in order to get 27, you're going to have to go and you're going to have to look at your list of powers of 3. So 3 to the exponent 0 is 1, 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. There it is. So in this case, x would have to be 3, because 3 cubed is 27. Or in exponential notation, 3 cubed is 27. We're going to try one, we're going to go the other way. 10 to the exponent x equals 10,000. Well, this is in exponential form. So I'm going to try and take this and convert it into logarithmic form. So I'm going to need to write the word log, because that's the function I'm using. Now, when this was a 2, a base 2 exponential, I used a base 2 logarithm. When this was a base 3 exponential, I used a base 3 logarithm. Now that this is a base 10 exponential, I'm going to need to use a base 10 logarithm. So I'm trying to ask myself then, log 10 of this number should give me this exponent. So log 10 of 10,000 should equal the number I don't know. And the real advantage to this is I don't have to guess and check this. Log 10 is a button on your calculator. So if you take a look at it right now, the square with the letters L-O-G on it, that's log base 10. So if you have this, you can just type log of 10,000, do it right now, and your calculator should spit out 4. So when I read this, as this sentence, what exponent would I have to put on a 10 in order to get 10,000? I get my sentence like this, and I can use the calculator and just push the button and I get 4. So in this particular question, x would be 4. So to use this in a more familiar algebra type context, I'm going to start with a question like this. 10 to some exponent equals 18. Now, 10 to the power 1 is 10, and 10 squared is 100. So I'm expecting a number between 1 and 2 as my answer. But up until this point, you have no actual way of calculating that. So now that the logarithm has been introduced to you, you're going to be able to use that button on your calculator to get exact answers without having to do any of the guessing and checking. So I have a base 10 exponential here, and I need to break that. The logarithm that breaks a base 10 exponential is a base 10 logarithm. So I'm going to apply log base 10 to both sides of this equation. And as with all function-antifunction pairs, when you apply them both to an x, they end up undoing each other. So log base 10 of a base 10 exponential is just x. And I have this thing over here, log 10 of 18. Now, you may recognize that as the little exercise I did a few minutes ago, where I took an exponential equation and I flipped it to its logarithm form. Either way you want to interpret this, it's up to you, whichever you see easiest. But in this, 10 to that exponent should be 18. That's exactly what I have written there. Now that I've got it down to this, I just have to pull the calculator out and recognize that this LOG base 10 is the LOG button available on my calculator. So if I get that out, then I find my log, clear, log of 10, nope, log of 18 equals 1.255272505. So what you just figured out is that 10 to the exponent 1.255272505 should give you approximately 18. So I'd encourage you to try that to double check your work. 10 to the exponent 1.255272505 equals 10 to the exponent 1.255272505 gives me 18 on the nose. Now there is a little rounding error here, but by the time I put all those decimal points in, the calculator just gives up and rounds it up to 18 for me. So I've been able to use this log button to solve base 10 exponentials. There is another button on your calculator that you can use to solve exponentials, and that's the one that says ln. So ln is the natural logarithm and it is a log. Ln is log base e. Now e is Euler's number, and that's a fancy thing from calculus, and when you get there you'll understand what it means and why we use it. But it is, for now, just an irrational number like pi. It's a universal constant. Lots of things in nature depend on it. So that's why it was grand enough to have made it to your calculator. So if you come across a question like this, e to the x equals 12. What that's asking you to do is to take Euler's number and find what exponent you would have to put on it to get 12. So if you're going to undo this, and the reason it's here, this is just on for an exercise in how to use logarithms. I see a funny number to some exponent, and I need to break that in order to solve this equation. You break exponentials by using logarithms. So I'm going to have to use a log, and because it's base e, I have to use log base e. If I apply it to this side, I have to apply it to this side as well. Now, as always, a function and its antifunction pair undo each other, and you're left with just the x. But over here, I have log base e of 12. Well, log base e is just ln, and you have that button on your calculator. So if I type that in then, ln of 12, sorry, this thing gets pronounced ln, ln. Lin is too hard to say. I end up with 2 0.48490665. So indeed, whatever this number is, it's a little less than 3. If you take a number a little less than 3 and raise it to that exponent, you would get 12 as your answer. So just to summarize how to use this particular set of functions, if I were to ask you what, say that the log base 5 of some number gives you 2.6, what is that number? Well, I'm going to have to use an antifunction pair in order to solve this. So the antifunction for a log base 5 is a base 5 exponential. So I'm going to take 5 and I'm going to raise it to this exponent. But if I do it on one side, I'm going to have to do it on the other. A function and its antifunction pair undo each other, so I'm left with just x on this side. And 5 to the exponent 2.6 is 65.663. 19511. Right. If I have them this way, base 4 exponential that I need to undo, the logarithm that undoes a base 4 exponential is a base 4 logarithm. And if you happen to have a calculator with a generic log button, you may be able to type this in directly, to calculate the log base 4 of 128. If not, we're still reduced to guessing and checking for this particular section. So 4 to the exponent 1 is 4. 4 squared is 16. 4 cubed is 64. 4 to the power of 4 is 256. Now, notice that this one is too small, because I'm looking for 128 and I only have 64. And this one is too big. So I'm hunting for a value between 3 and 4. Well, if you like, just try 3.5. That's halfway through. So 4 to the exponent 3.5 gives me 128. Perfect. So it turns out that log base 4 of 128 is 3.5. So this base 4 logarithm and base 4 exponential undo each other, and the value of log base 4 128 is 3.5.